Hi, my name is Bailey Chambliss, and this is my Physics 2211 lab number 3, black hole. So the purpose behind this lab is to find the mass of the black hole and the time between points in the trajectory, and to predict the motion of the planet and the spaceship through the calculation of all gravitational forces. So in part 1, we calculated the mass of the black hole using Newton's second law, and in part 2, we find an initial velocity for the spaceship using trial and error. So our results came back that the mass of the black hole was determined to be 8.7 times 10 to the 33 kilograms, and the possible initial velocity was determined to be -4 times 10 to the 7th in the x direction, 1.86 times 10 to the 6th meters per second in the y direction, and 0 in the z direction. So our fundamental principles used in this lab are Newton's second law, which says that the chain dp equals f net delta t, so dp dt equals the equation given, and then the instantaneous rate of change of momentum is given as below. And our diagram on the right shows this visually. So in our first part, this is our glow script model where our system is the star, the surroundings are the black hole in space, and our initial conditions are that the star is orbiting the black hole in a counterclockwise motion. Delta t is 1 day, and that's given in seconds. And then the mass of our star is 2 times 10 to the 30th kilograms, and that was given in the instructions in the lab. And then Newton's second was used to calculate the net force, the perpendicular component of the net force, and the parallel component of the net force. And that can be seen in the code on the left-hand side. And then the mass of our black hole was calculated with the equation below, the absolute value or the magnitude of the net force times the magnitude of the vector squared over the gravitational constant times the mass of the star. So in part 1, our results were that the mass of the black hole was determined to be 8.7 times 10 to the 33 kilograms. The net force was determined to have a magnitude of approximately 7.6 times 10 to the 28th newtons. The parallel component of the net force was determined to have a magnitude of 1.19 times 10 to the 28th newtons. The perpendicular component of the net force was determined to have a magnitude of 7.5 times 10 to the 28th newtons. And some possible sources of error include the fact that the approximations were made in each iteration of the code because the mass of the black hole changes in every iteration. So in part 2, our system was a spaceship, our surroundings were the planet and the black hole. Our initial conditions were that the direction of the motion from the planet is in the plus y direction, and the mass of the black hole is what we calculated in the last part. The mass of the planet was given, and then the mass of the ship is also given. And then in the equation below, you can see that the equation for net force is given out below. So in part 2, our results, after using trial and error, it was determined that the initial velocity, -4 times 10 to the 7th meters per second in the x direction, 1.86 times 10 to the 6th meters per second in the y direction, and 0 meters per second in the z direction, allows the spaceship to leave the system without hitting the planet or being pulled in by the gravitation of the black hole. Some possible sources of error include human error by incorrect trial of initial velocities. So our discussion questions. What does it mean? Even though F net, including its components, both perpendicular and parallel, and the rate of change of motion are not different mathematically, they require different components in order to solve. So in this experiment, the rate of change of momentum uses velocity and mass to solve as a function of time, while F net cannot be solved without knowing the mass of the black hole. So basically we had to do part 1 in order to be able to successfully do part 2. So, and then what if, using some trial and error to determine what initial velocity would mean that the spaceship was able to enter orbit with a black hole, it was determined that with the initial velocity, -4 times 10 to the 7th in the x meters per second in the x direction, 1.3 times 10 to the 7th meters per second in the y direction, and 0 in the z direction, would be sufficient velocity for the spaceship to enter orbit around the black hole without crashing.